Greetings and good time of day to you. I've been repairing rather a lot of Spectrum computers lately, and here's another one that's been sent to me. All its owner has told me is that he's not been able to get a picture on a television connected to its RF video output. The case is a bit bashed about, etc., particularly on the underside, and you can see that two of the keys from the cassette deck have gone missing. Well, in fact, I have the two keys here, and they've snapped off at this point. Perhaps I'll be able to find a way to reattach them, but I think it will be rather difficult, as the part where it's broken carries the full force of the key being pressed. Anyway, first of all, I'll remove the main circuit board from inside and start by inspecting that. I've unplugged the 5-volt regulator which is mounted on this heatsink here, and I must keep reminding myself to reconnect that before I power the Spectrum on to test it, because that's something I often forget to do when working on these computers. Straight away I noticed that almost all of the smaller ICs, including all of the RAM, are fitted in sockets, and I don't think that's how they originally would have been. The owner tells me this Spectrum was previously repaired, I think sometime during the 1990s, so that probably explains that. It looks as if here the repairer didn't have a socket of the correct size, so I suppose this is a reasonable compromise, but I probably would have cut off this excess part. And over here, someone's made a terrible mess of things. I'm surprised that it was necessary to replace so many ICs in order to repair this. In fact, I suspect it wasn't really needed. Let's have a look on the underside. I think this is a factory modification to do with the connection for the audio carrier. However, I'm not so sure about these two resistors. I'll have to check the circuit diagram and work out what they could be for. And this wire jumper here, that's clearly to repair a track that was damaged while removing the RAM ICs. But particularly worrying is something that's happened over here. A terrible mess has been made of the circuit board, and multiple pads have been removed from the surface. Now it can be a bit tricky to avoid damaging the traces or the pads when removing ICs, although with a bit of care and the correct technique it's certainly possible to avoid it. And strangely that doesn't seem to have happened in many cases for the ICs on this board. But over here these components are just resistors and diodes, as we saw earlier on the other side. And pad after pad after pad has been ripped off the board. I really can't imagine how someone managed to do that. I've reconnected the voltage regulator, and I'll very quickly take a couple of resistance measurements to make sure there are no short circuits across the power supply rails. I connect the common lead of the multimeter to the 0-volt power supply input via this lead. And first we'll check the resistance across the DC input. Even on the 4 megohm range it's reading open circuit, so it's certainly not shorted. Let's check we have the 0-volt connection onto the circuit board, and yes, we have there. And the 5-volt connection should be here. 200 and something ohms, and it's become fairly steady. I think that's okay. That should be relatively low, but there's not a dead short circuit. Now, unlike the 48K Spectrums, the RAM in the 128K models only uses the 5-volt power supply. It doesn't require the minus 5-volt and 12-volt supplies. However, in the 128K Spectrums, there is a voltage converter circuit over here on the circuit board that's very similar to the ones in the 48K models, and that generates 12 volts that's used by the composite video generator and I think the serial ports. However, I'm not too worried whether or not that's working at the moment, because if it isn't, there'll be no composite video output, but there'll still be an RGB TTL output, and that'll be good enough for the time being. I have a 9-volt power supply connected, though not yet switched on, and this multimeter ready to measure voltages. So let's switch on and see what happens. The power supply says it's drawing approximately 1 amp, which doesn't seem particularly excessive. Here we should find the 5-volt supply. Yes, that's correct. And if the voltage converter circuit is working, then there should be approximately 12 volts on pin 11 of the composite video generator. That's perhaps slightly low, but probably acceptable. I'm certainly not going to worry about that for now. I also have this oscilloscope ready, and let's have a look at a few key points to see what's going on. So to start with, I'm going to connect it to the Z80's clock input, which is pin 6. And that's a good sign. There is a clock signal there. It also appears to stop at regular intervals. That might seem like a bad thing, but no, that's a very good sign. That suggests that the ULA is correctly blocking the clock at regular intervals, well, when necessary, to prevent contention of the lower RAM. Let's have a look to see whether the ULA is generating a video signal. So first we'll look directly at the ULA. On pin 19, I think, is the one I need, which is its blue TTL output. This one here. Adjust the oscilloscope's time base. And that looks something along the right lines. So everything's very promising so far. Let's see whether there's a composite video signal. So I need to look at pin 6 of this IC over here. So it looks something like a composite video signal. It's not very clear though. I think that is a valid composite video signal, either with some unwanted interference, or I suspect we'll find this signal here is the 6 MHz audio carrier. I've also noticed that this connector here to the voltage regulator is making a rather poor connection. For example, the power is switched on and the multimeter is connected to the 5-volt power supply rail. You can see 5 volts. Do I move this just slightly? And the connection is disrupted. So I need to do something to remedy that. I removed the 3 contacts from this plastic block by gently pushing in on the spring with a small screwdriver and sliding them out. I then carefully scraped the contact surface of each and did the same to these pins here to remove any surface contamination. I applied some contact cleaner, have reassembled it, and now I find the connection is perfectly stable. I've connected the Spectrum's RF video output to a television, so let's see whether we can get a picture. I'll adjust the television's tuning. There we have it. It's not a particularly good quality picture. The RF video output from these computers doesn't normally produce a great picture, although this is a bit worse than usual. However, it suggests the computer is at least mostly working. I've now connected a keyboard, and yes, I'm aware that some of the menu options are in Spanish. This Spectrum's owner told me that it has a Spanish version of the ROM fitted. So let's see whether it'll respond to keyboard presses. Seems to be working well. Now if I turn the television's volume up, should be able to hear a click with each key press. Which I can't. So I try holding down the brake key and pressing the reset button, which puts the Spectrum into a test mode that shows this picture, and it should produce an intermittent beeping sound, but I can't hear that. So maybe there's a problem with the audio production, or for some reason the television just isn't picking up the audio carrier. While clearing the keyboard away, I was surprised that a fingertip came into contact with something painfully hot. It turned out to be this resistor down here, R79. It certainly shouldn't be getting hot, and further investigation has uncovered something very strange. If I connect the oscilloscope probe to this point here, this is the 12-volt output of the voltage converter circuit. And there should be a fairly steady 12 volts at that point, perhaps with a bit of ripple on it. Have a look, that's clearly not the case here. There's this signal with an amplitude of 20 volts or so peak to peak at 80 something kilohertz. The average is around 10 volts, that probably explains the voltage the multimeter read when I connected it to the 12 volt supply rail earlier. If I now put the probe onto the collector of transistor TR8, there's just a steady voltage there. And that's not right either. That suggests the voltage converter circuit isn't oscillating as it should do. For comparison, here's a capture of the waveform that should be present on TR8's collector, taken from a working +2. I've removed most of the components that make up the voltage converter circuit, including transistors TR8 and TR9. I used a multimeter to make a quick test of all of those components other than the electrolytic capacitors, and that didn't uncover any obvious faults. I've got a dual-channel bench power supply set up to feed in 5 volts to this point here, which is where the voltage regulator would normally connect, and 12 volts over here. That supply would normally be generated by the voltage converter circuit, which of course is now missing. So let's switch on and see what happens. The supply says it's drawing about 600 milliamps at 5 volts and just under 100 milliamps at 12 volts. There's a bit of interference on the picture and the usual yellow and cyan ghosting effect, etc. But that's not too bad, that's about what I'd expect from the RF output of a +2. Here's the voltage converter circuit diagram taken from the +2 service manual. The external approximately 9 volt power supply enters on the left here. This optional common mode inductor isn't present in this +2. I imagine it was required in some markets to comply with RF emission standards. Instead, in this case, links 5 and 6 are in place to connect the input voltage directly to the 5 volt regulator. Now there's clearly a mistake on this diagram. The 5 volt output here is not connected up to this point, but it is connected over to here where it's labelled 5 volts to the emitter of transistor TR8. This resistor here, R55, forms a feedback connection from the 12 volt output around to the base of TR8. This means that if the 12 volt output is too high, then TR8 tends towards switching off, and if it's too low, TR8 turns on more. This controls the current fed to the oscillator part of the circuit, which in turn controls its frequency, and so maintains the output at 12 volts. A convenient way to check whether the circuit is oscillating as it should is to connect an oscilloscope to TR8's collector, as I did earlier. I don't think the transistor that was installed for TR8 was the original one. I found a BC307 in that position, which I think is a reasonable substitute for TR8, and it was installed the right way around. However, over here, TR9, I found a BC374, Also installed the correct way around, but I don't think that is an appropriate replacement for a ZTX 650. Certainly its current handling capability is significantly worse. However, a quick check with a multimeter suggested that neither of the transistors was faulty. Of course, I will eventually replace this transistor here with a new ZTX 65 something. This 100 ohm resistor here, R79, is the one that was overheating, and I'm struggling to work out quite why that could have been happening. Something must have been causing excessive current to flow through it. Of course, given all the damage to that area of the circuit board, it's quite possible the components were not connected up as shown in this diagram. I fitted a total of 25 small metal eyelets, like these ones here, to repair damaged plated through holes. In most cases, the component leads would fit through the smaller size of eyelet, and these also fitted snugly into the existing holes. However, diodes D19 to D22 have thicker leads, so I had to use a larger size of eyelet, and in those cases it was necessary to slightly enlarge the holes with a small drill. I've made a quick pass of soldering the eyelets to their connecting tracks where appropriate, though in some cases the solder didn't take very well, so I'll apply some additional flux and put that right as I go through and reinstall the components. In a perfect world, the eyelets would fit without fouling any adjoining tracks or pads, but of course that didn't always happen, and so in some cases it was necessary to trim bits off or bend one end of them into a non-circular shape. So the end result isn't quite as neat as I'd like, but of course the most important thing is that they make the correct electrical connections and provide support for the components. I've already reinstalled these two diodes here, and because they're connected in series, I didn't bother fitting eyelets on this side. I've simply soldered their leads together. Also, capacitor C39 down here was held in place only by being soldered to the two tracks that connect it over to transistor TR8, and they broke when I removed it, so I'll have to lay down a couple of short lengths of wire to repair that damage when I fit a new capacitor for C39. So next I'm going to refit all the components one by one, making careful continuity checks as I go to make sure they're all connected as they should be and there are no unwanted shorts. I've refitted all of the components, and given the extent of the damage I had to repair, I think it's looking rather good now. I fitted all new electrolytic capacitors, even though I tested the ones that I'd removed and couldn't find anything wrong with them. And if this circuit now works, I'll go ahead and replace all the other electrolytic capacitors in this spectrum, because most of them look like the originals, and I want to make sure they won't be the cause of any failures in the foreseeable future. I've used a new resistor here for R79, because while the one that I removed still measured 100 ohms, its body was rather blackened from its overheating. And as I said I would, I fitted a ZTX 653 over here for TR9, and here for TR8, while the one that I removed I think should work here, I fitted a new BC557, as I know for certain that should work in this circuit. As I refitted the components one at a time, I found one track that was broken where it passed through a damaged component mounting point, and that meant that this Zener diode here and capacitor C22 had lost their connection to the 0 volt point. I don't know whether that damage was present when I received the Spectrum, or whether it was due to my repair of that hole by fitting an eyelet. However, I scraped off a little of the solder mask from the tracks either side, and then made sure that both were soldered to the eyelet. So, I've got a 9 volt power supply connected, but not yet switched on, and this oscilloscope probe is connected to TR8's collector, so I'll be able to see what's happening at that point straight away. So I'll switch the power on now. And that waveform on the oscilloscope looks, I think, more or less how it should do. That's a big improvement over before. That suggests this circuit's now working properly. Let's quickly use this voltmeter to check the voltage at the output, at the 12 volt output of the voltage converter circuit, this point over here, which, remember before, had a strange waveform present and only measured about 10.5 volts or so. That's much better. So 12 volts is present there. Let's have a look at that point with the oscilloscope. I will turn the power off to make sure I don't cause a short circuit at TR8 while I disconnect this probe. And I'll adjust the vertical scale on the oscilloscope to something more appropriate. Turn the power on again and connect this probe to the 12 volt output. The strange oscillation that had been going on there before has now gone, so it looks as if this circuit's working properly. Resistor R79 is slightly warm, but it's not burning my finger, so I think that's perfectly alright too. And here's the display on the connected television. It looks about the same as it did when I used an external 12 volt power supply, so I think again this confirms that the voltage converter circuit is now working properly. I think that some of the picture degradation is due to a poor connection at the Spectrum's RF modulator output. For example, if I move the plug at that point, even very slightly, you can see it has a fairly dramatic effect on the picture. It looks as if the modulator is made of a plated metal, and much of that plating has worn away on the output socket, so I don't think I'll be able to do much about this, but I believe the owner of this Spectrum intends mainly to use the composite or RGB outputs, so hopefully this won't be a major problem.